Here's the next question, number 24. A 4-pole lap-connected, separately excited DC motor is drawing a steady current of 40 amps while running at 600 rpm. A good approximation for the wave shape of the current in armature conductor of the motor is given by. So this is a multiple choice. We have been given 4 choices of different waveforms. Now we have to choose the right waveform in order to determine the current in armature conductor. So let's begin with what's given to us. A 4-pole. So pole P is equal to 4. Now you see lap connected. Lap connected should tell you that the number of parallel paths is equal to the number of poles. So parallel paths is denoted by A. A is equal to 4. Okay. So the next thing given to us is the speed. Now we have been given that the speed is 600 rpm. Now let me tell you how to determine the time period. There are actually 2 ways by which we can find out the time period of a waveform. So before we go into that, let's find out what is the time taken to complete 1 revolution. So it is given that the speed is 600 rpm. For 600 revolutions, it is 1 minute. So 60 seconds. How much would 1 revolution be for? So 1 revolution would give us a ratio of 60 by 600, which is 0.1 second. Okay, which means that for every 1 revolution, it takes 0.1 seconds. Now the total current in the question is 40 amps. So the total current is 40 amps, the current that is passing through, the steady state current. So since we have also been given the number of parallel paths, that is lap connected, now that should tell us that we need to find out the current in each parallel path. So the current in each parallel path would be the total current divided by the number of parallel paths, 40 by 4, which gives us 10 amps. Now because the current in each parallel path is 10 amps, that should tell us that option B is not the right one, because here it's given that there is a direct current of 40 amps. So that is wrong. Now the current in each parallel path is 10 amps, which leaves us with the options of A, C and D. Okay, the next is to find out the time period. Now you'll notice that in each of the waveforms, the x-axis denotes the time. So to find out the time period, we can use one of 2 methods. One method is to use the speed that is given to us and find out the time period through that. Or we can find out by calculating the pole pitch. Okay, so the pole pitch is the distance from center to center between 2 adjacent poles. It is good to keep a note of that as well. So we find out the time period for 1 pole pitch. In other words, it is the time period for 1 half wave or 1 half cycle. Sorry. Okay. So I'll show you both the methods. The first method over here is by taking speed into consideration. We have been given that the speed is 600. So we know the basic formula N is equal to 120 F by P. So from this, we can say that F is P times N divided by 120. The number of poles 4, N is 600 divided by 120, and to solve that, we get 20 Hertz. So if the frequency is 20 Hertz, we can calculate the total time period of 1 complete cycle. F is 1 by T. So T is 1 by F. So 1 by F is 1 by 20, which gives us 50 milliseconds. Now the next type is to calculate the pole pitch. For 1 pole pitch, the time period is time of 1 revolution divided by the number of poles. Now in the previous part, we found out the time of 1 revolution here. Let me just show that to you. Right, over here. 1 revolution is 60 by 600, which is 0.1 second. So if you substitute the values here, T equals 0.1 divided by 4, that's 25 milliseconds. So either you can find out the time period of 1 complete cycle or the time period of half a cycle. So that's 50 milli and 25 milli. So once you find out half a cycle, you can easily tell that one full cycle is twice this amount. Okay, so these are the two ways. Now because you can find out the time period, it tells us that option A is also wrong. So we are left with option C and D. You will notice that each of the time periods is 50 across an entire cycle. So for linear commutation, this talks about DC motor, a separately excited DC motor. So for a separately excited DC motor, and that too for lap connected winding, you should know that the linear commutation and the change of current values from 10 amps to minus 10 amps is a straight line. So because it is a straight line, number C is the right option. I hope this has helped.